A black hole is not born out of nothing. It appears when a massive star reaches the end of its life and the balance that kept it in existence suddenly vanishes. For millions of years, a star functions like an immense nuclear reactor. At its center, temperatures that can exceed 15 million degrees allow hydrogen to fuse into helium. This reaction releases a gigantic amount of energy and creates a pressure that pushes outward. But another force is constantly acting in the opposite direction: gravity. All of the star's mass is continually trying to collapse in on itself. The very existence of a star therefore rests on an extremely fragile balance between two opposing forces: the nuclear pressure that pushes outward and gravity that crushes inward. In the Sun, this balance has lasted for about 4.6 billion years. Every second, our star transforms about 600 million tons of hydrogen into helium and converts nearly 4 million tons of matter directly into energy, according to Einstein's equation: E equals mc squared. This energy is so immense that in a single second, the Sun produces more energy than all of humanity has throughout its entire history. But the most massive stars live much faster. Some have a mass 20, 30, or even 100 times greater than the Sun's. Their gravity is so intense that they consume their nuclear fuel at a gigantic rate. Where the Sun can live about 10 billion years, some massive stars collapse after only a few million years. And the further they progress in their lives, the more they fuse heavier elements: hydrogen, helium, carbon, oxygen, silicon, up to iron. And that is where the catastrophe begins. Iron represents a fundamental limit in stellar physics. Fusing iron nuclei no longer releases energy, it absorbs it. In other words, the star suddenly loses the force that was resisting its own gravity. In just a few seconds, the core collapses. Matter plunges toward the center at speeds that can reach several tens of thousands of kilometers per second. By comparison, some parts of the core collapse at nearly 25% of the speed of light. The density then becomes unimaginable. Atoms are literally crushed. Electrons merge with protons to form neutrons. A single teaspoon of this material could weigh several billion tons on Earth. Meanwhile, the star's outer layers rebound violently off this ultra-compressed core and trigger a supernova explosion. A single supernova can briefly become brighter than an entire galaxy containing hundreds of billions of stars. In a few seconds, it releases more energy than the Sun will during its entire estimated 10 billion year lifetime. It is also in these explosions that most of the heavy elements in the universe are formed: gold, uranium, calcium, the iron in our blood. In other words, the atoms in our bodies come from dead stars. But sometimes, even the explosion is not enough to stop the collapse. If the remaining core exceeds about 2 to 3 solar masses, then even neutron pressure becomes insufficient. No known force in the universe can resist gravity. The collapse continues, again and again, until matter is compressed into a region so dense that the speed required to escape it exceeds 300,000 kilometers per second, the speed of light. And according to modern physics, nothing can go faster. From that moment on, a boundary appears in space, an invisible limit called the event horizon, the point of no return. Once that boundary is crossed, nothing can come back out. Not matter, not light, not information. A black hole has just been born. For billions of years, black holes remained invisible. Not because they were rare, but because they produce almost no light. And yet today, astronomers know they are everywhere in the universe. At the center of most known galaxies lies a supermassive black hole. The Milky Way itself has one, Sagittarius A star, located about 27,000 light-years from Earth. Its mass is estimated at about 4 million times that of the Sun. And some black holes go even further. The black hole at the center of the galaxy M87 has a mass of about 6.5 billion suns. Its event horizon is so immense that several solar systems could fit inside it entirely. But despite these gigantic dimensions, one fundamental problem remains. We never see a black hole directly. We observe only its effects. When a black hole attracts matter, that matter doesn't fall straight inside. It first starts orbiting the black hole at extreme speeds, forming what's called an accretion disk. In this region, gases reach monstrous temperatures. Through friction and gravitational compression, some areas exceed several million degrees. At these temperatures, matter becomes an ultra-energetic plasma, capable of emitting X-rays detectable from Earth. That's how astronomers discovered the first black hole candidates, not by seeing them directly, but by observing stars being invisibly devoured by something extremely massive. In some binary systems, a star orbits an invisible companion. By analyzing its speed and trajectory, scientists realized that a massive object was present, without emitting light. And sometimes, the effects become even more violent. When a star passes too close to a black hole, the differences in gravity become extreme. The part of the star closest in is pulled much more strongly than the part farther away. Result? The star is literally torn apart. This phenomenon has a name: a tidal disruption event. Gravitational tidal forces stretch the star until it turns into a long filament of matter heated to millions of degrees before it is gradually absorbed. Some simulations show that this destruction can temporarily release more energy than an entire galaxy. And yet, that's still only the outside of the black hole. Because as you get closer, the normal rules of the universe begin to break down. According to Einstein's general relativity, gravity doesn't merely pull objects. It literally warps space and time themselves. The stronger the gravity, the more extreme that warping becomes. On Earth, this effect already exists. Time passes slightly more slowly at ground level than at higher altitudes. GPS satellites even have to correct this difference constantly. Without relativistic corrections, their calculations would drift by several kilometers per day. But near a black hole, this effect becomes colossal. If someone watched an astronaut slowly approaching the event horizon, they would see something strange. The astronaut would seem to slow down progressively. Their movements would become slower and slower. Their light would become redder. Then they would seem almost frozen in time, as if the black hole were literally slowing their existence. But from the astronaut's point of view, nothing special would happen immediately. For them, time would continue normally. This apparent contradiction is real. Two observers can measure completely different times depending on their position in the gravitational field. And the closer you get to the black hole, the more extreme this difference becomes. Near certain supermassive black holes, a few minutes spent close to the horizon could correspond to whole years far from the black hole. Time itself ceases to be universal. But gravity doesn't only warp time. It also warps light. Around black holes, light rays follow curved paths through the distorted space-time. This is called gravitational lensing. Light from objects behind the black hole can be bent all the way around it, producing luminous rings called Einstein rings. Some simulations even show that an observer nearby could see the back of their own head, simply because the light would go around the black hole before returning to them. Space becomes so distorted that normal notions of direction begin to lose their meaning. And then comes the most terrifying effect of all: spaghettification. This phenomenon is caused by gravitational tidal forces. If a person fell toward a stellar mass black hole, their feet would be pulled much more strongly than their head. The difference in gravity between the two ends of the body would become enormous. The result would be catastrophic. The body would be stretched progressively over thousands of kilometers, while its width would be compressed, atom by atom, cell by cell, like an extremely thin filament of matter. And this process could begin well before even reaching the event horizon for small black holes. But paradoxically, some supermassive black holes could allow you to cross the horizon without immediately feeling this destruction. Because their horizon is much larger, the gravitational gradients there are less brutal locally. And that is precisely where the true nightmare begins. Because once that boundary is crossed, no current theory correctly describes what is really happening. For billions of years, this star maintained an almost perfect balance between two opposing forces. On one side, gravity, a gigantic force that constantly tries to crush the star in on itself. On the other, the pressure produced by nuclear fusion. At the core of the star, hydrogen nuclei fuse to form helium, releasing an absolutely colossal amount of energy. Every second, the sun transforms about 600 million tons of hydrogen into energy. And yet, the stars capable of becoming black holes are far more extreme. Some have a mass 20, 50, sometimes even more than 100 times that of the sun. Their core reaches temperatures of several tens of millions of degrees. At those levels, matter no longer behaves as it does on Earth. Atoms are completely ionized. Electrons are torn away. Matter becomes an ultra-dense plasma dominated by constant nuclear reactions. But this balance is not eternal. The more massive a star is, the faster it consumes its fuel. The Sun will live about 10 billion years. Some giant stars, on the other hand, exhaust their fuel in only a few million years. On the cosmic scale, that's almost instantaneous. And when nuclear fuel begins to run out, everything shifts. Fusion slows down, internal pressure decreases, and suddenly, nothing truly opposes gravity anymore. The star's core then begins to collapse in on itself at a dizzying speed. In just a few seconds, a core sometimes more massive than the entire sun is brutally compressed. The star's outer layers plunge toward the center at speeds that can reach tens of thousands of kilometers per second. Then comes one of the most violent events in the observable universe: the supernova. An explosion so powerful it can briefly outshine an entire galaxy containing hundreds of billions of stars. For a few moments, a single star can emit more energy than the sun will during its entire life. Shock waves race through space for billions of kilometers. Heavy elements like gold, uranium, or iron are blasted into the galaxy. The iron in your blood probably came from ancient supernovas. But despite this gigantic explosion, the star's core keeps collapsing. And this is where physics becomes almost incomprehensible. Because beyond a certain mass threshold, nothing can stop the collapse. Not nuclear reactions, not atomic pressure, not even the known quantum forces. Matter is compressed into an ever smaller space. Imagine compressing a mass several times greater than the Sun into a region sometimes smaller than a city. The density becomes so extreme that space-time itself begins to warp massively. It's not only matter that collapses, it's the very structure of the universe around the object that begins to change. According to Albert Einstein's general relativity, gravity is not simply an invisible force. It is a curvature of space-time. The more mass an object has, the more it distorts reality around it. And in the case of a black hole, that distortion becomes extreme. Imagine placing a heavy ball on a stretched sheet. The sheet deforms slightly. Now imagine a gigantic stellar mass compressed into a tiny space. The deformation becomes so deep that once a certain limit is crossed, nothing can climb back out. Not even light. And that boundary has a name: the event horizon. The absolute point of no return. An invisible boundary surrounding the black hole. If an object crosses this limit, no speed known in the universe makes it possible to come back. Even light, which travels at about 300,000 kilometers per second, remains trapped. That is precisely why a black hole is black. We cannot see the object itself directly, because no light information can escape. But paradoxically, black holes are among the brightest objects indirectly observed in the universe. Because before disappearing behind the event horizon, matter circles the black hole in an accretion disk. And this disk becomes hellish. Gases there reach millions of degrees. Particles collide at relativistic speeds. Ultra-energetic X-rays are emitted in all directions. Some supermassive black holes at the centers of galaxies produce plasma jets thousands of light years long. Structures so gigantic that they sometimes exceed the entire size of certain galaxies. And yet, all of this happens only on the outside. Because once the horizon is crossed, no direct observation is possible anymore. The universe literally forbids us from seeing what happens next. For billions of years, this star maintained an almost perfect balance between two opposing forces. On one side, gravity, a force that constantly tries to crush all matter toward
the center. On the other, the immense pressure produced by nuclear fusion. At the heart of the star, hydrogen nuclei fuse to form helium, releasing an absolutely colossal amount of energy. Every second, our sun transforms about 600 million tons of hydrogen into helium. And despite this unimaginable consumption, it can keep going for about 10 billion years. But the most massive stars live much faster. Some have a mass 20, 50, or even 100 times greater than the sun's. And the more massive a star is, the faster it burns its fuel. Some die after only a few million years. On a cosmic scale, that's almost instantaneous. Because at the center of these stars, the temperature exceeds tens of millions of degrees. The pressure becomes so extreme that nuclear reactions run out of control. The star then begins to fuse heavier and heavier elements: hydrogen, helium, carbon, neon, oxygen, silicon, until it reaches a very particular element: iron. And that's where everything tips over. Because unlike the other elements, fusing iron no longer produces energy. On the contrary, it consumes it. In other words, the star reaches the end of what was keeping it alive. The core gradually stops producing the pressure needed to resist gravity. And for a fraction of a second, the balance that had lasted millions of years disappears. Imagine a mass several times greater than the Sun, suddenly beginning to collapse in on itself. The core collapses at a staggering speed. The outer layers fall toward the center at thousands of kilometers per second. Matter is compressed with a violence that's hard to imagine. Electrons and protons fuse. Atoms themselves cease to exist normally. In some supernova, the star's core collapses until it reaches only a few dozen kilometers in diameter. A mass, sometimes greater than the Sun's, compressed into a region smaller than a city. And the energy released during this collapse is monstrous. A supernova can briefly produce more light than an entire galaxy containing hundreds of billions of stars. In just a few seconds, it releases more energy than the Sun does over its entire lifetime. And yet, even this titanic explosion is sometimes not enough to stop the collapse. If the remaining core has too much mass, nothing can stop gravity. Absolutely nothing. Not matter, not atomic forces, not nuclear pressure. The collapse continues, again, 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 until a point where the density becomes almost incomprehensible. To give an order of magnitude, if Earth became a black hole, its diameter would shrink to about 9 millimeters. The entire planet compressed into something smaller than a coin. For the Sun, you'd have to reduce it to a radius of about 6 kilometers. And the more matter collapses, the more violent gravity becomes. But what makes black holes truly terrifying isn't simply their density. It's their effect on space itself. According to Einstein's general relativity, gravity isn't a classical force in the usual sense. It's a deformation of space-time. A planet like Earth slightly warps the space around it. The Sun warps it much more. But a black hole literally deforms the very structure of reality. Imagine placing a ball on a stretched fabric. The fabric curves slightly. Now imagine a gigantic mass concentrated in a tiny region. The curvature becomes extreme. Around a black hole, space almost stops working normally. Light itself begins to follow warped trajectories. Time slows down. Distances change. And there is a very precise boundary where everything becomes irreversible. This boundary has a name: the event horizon. It's the point of no return, the limit beyond which nothing can escape. Not a spacecraft, not a planet, not even light. Because at that point, the speed required to escape exceeds the speed of light itself. And according to everything we know today, nothing in the universe can go faster than light. This means that once this boundary is crossed, all escape disappears. But the strangest part is that from the outside, an observer would never actually see someone cross that horizon. Because of relativistic effects, time would appear to slow down gradually. The object would seem to become slower and slower, redder and redder, until it almost freezes, as if the black hole were holding time itself back. And that is only the beginning of the problem. Because everything we have just described concerns only what
happens around the black hole, not inside it. And that is precisely where physics begins to break down. What really happens after the event horizon? It is probably one of the deepest questions in all of modern physics, because beyond that boundary, no direct observation is possible. Everything science describes after that rests on equations, mathematical models, and theories that, at that exact point, begin to contradict one another. And at the center of the problem is a word that physicists dread: singularity. According to the current equations of general relativity, all the matter that crosses the event horizon continues collapsing toward a point of infinite density. A place with a volume becomes theoretically zero,
and where the density becomes infinite. But in physics, an infinity is often a sign that something is no longer working correctly in the equations. It is as if the mathematics itself were announcing a breakdown in understanding. Because an infinite density probably has no real physical meaning. It mainly means that our current models become incapable of describing what is really happening. And that is where the greatest conflict of modern physics begins. On one side, Einstein's general relativity, an extraordinarily precise theory for describing gravity, planets, stars, galaxies, and the overall structure of the universe. On the other, quantum mechanics, the theory that describes the behavior of subatomic particles with almost perfect precision. The problem is that these two theories are incompatible under the extreme conditions of a black hole. On large scales, relativity works perfectly. On very small scales, quantum mechanics works perfectly. But at the heart of a black hole, both must act simultaneously. And when one tries to combine them, the equations literally blow up. The results become absurd. Infinite energies, infinite curvatures, infinite densities. As if the universe reached a zone where our current laws of physics cease to be sufficient. To understand how extreme this region is, we have to talk about the curvature of space-time. On Earth, gravity slightly distorts the space around us. The Sun does so much more strongly. But near the singularity, the distortion becomes theoretically infinite. Imagine taking a perfectly flat sheet of paper, then bending it slightly, then more still, until you tear it completely. That is roughly what the equations predict for spacetime inside a black hole. The very structure of reality could collapse, and time itself becomes a problem. According to certain solutions to Einstein's equations, after crossing the event horizon, going toward the singularity becomes as inevitable as moving into the future. On Earth, we all move through time without being able to stop it. Inside a black hole, the singularity could become an unavoidable temporal destination. In other words, beyond the horizon, the center of the black hole might no longer be simply a place in space, but a direction in time. And it is precisely this kind of idea that makes black holes so unsettling, because they break our fundamental intuition about reality. But the problem becomes even stranger when we talk about information. In modern physics, an essential rule exists. Information cannot be destroyed. And that is exactly the problem that has obsessed physicists for decades: the information paradox. In the 1970s, the physicist Stephen Hawking discovered something even more troubling. According to quantum effects, black holes are not completely black. They emit a very faint radiation today called Hawking radiation. This phenomenon is linked to quantum vacuum fluctuations. Even the absolute vacuum is not truly empty. Particles constantly appear and disappear on microscopic scales. Near the event horizon, some of these particles could be separated. One falls into the black hole, the other escapes into space. Result: the black hole gradually loses energy. It evaporates slowly. But this process creates a gigantic problem. Because if a black hole ends up disappearing completely, what happens to all the information that fell inside? Destroyed? Transformed? Stored elsewhere? For decades, this paradox has pitted some of the greatest physicists in the world against each other. And some proposed solutions become almost stranger than black holes themselves. Some modern theories suggest that the singularity may not even really exist, because in reality, Einstein's general relativity does not incorporate quantum effects. Yet near the center of a black hole, distances become so small that quantum phenomena should become dominant. The problem appears around what is called the Planck scale. It is a fundamental limit of physics located around 1.6 times 10 to the minus 35 meters. At this size, space-time might no longer be continuous. It could become granular, fluctuating, unstable. For comparison, a proton measures about 10 to the power of minus 15 meter. The Planck length is therefore about 100 quintillion times smaller than a proton. At this scale, quantum fluctuations of gravity become theoretically enormous. Space itself could foam, vibrate, or change structure. And that means that at the center of a black hole, the infinite singularity predicted by relativity could be replaced by something else. Some approaches, like loop quantum gravity, suggest that a total collapse is impossible. Compression would stop before infinity thanks to extremely powerful repulsive quantum effects. In some models, the core of the black hole could bounce back, a bit like a cosmic spring compressed to the maximum. And that's where a fascinating hypothesis appears: white holes. A white hole would theoretically be the inverse of a black hole. Instead of absorbing matter, it would expel it. According to certain solutions of the Einstein-Rosen equations, a black hole could be connected to a white hole via an Einstein-Rosen bridge, better known as a wormhole. Mathematically, these structures do indeed appear in certain relativistic equations. The problem: they seem extremely unstable. The slightest gravitational perturbation could make them collapse almost instantly. To keep a wormhole open, some theories require exotic matter with negative energy density. And to this day, no direct experimental evidence of this matter exists. But some quantum observations show that negative energy effects can appear locally. For example, with the Casimir effect. When two extremely close metal plates are placed in the quantum vacuum, certain fluctuations are blocked between them, creating a measurable difference in vacuum pressure. This phenomenon has been confirmed experimentally, and it shows that the quantum vacuum is far stranger than it seems. Other hypotheses go even further. Some versions of cosmology suggest that our entire universe could have been born inside a black hole. The idea rests on a troubling point. The equations describing the universe's initial expansion sometimes mathematically resemble those describing extreme gravitational collapse seen from another frame of reference. In some models, when a singularity forms, it could generate a new expanding spacetime. In other words, a baby universe. That would mean that each black hole could potentially contain an entire universe inaccessible from the outside. And our own universe could itself be located inside a black hole belonging to another, larger universe. This idea remains speculative, but certain real cosmological properties fuel the debate. For example, our universe has a density extremely close to the critical density required for an almost flat geometry. Measurements from the Planck satellite show that the observable universe is remarkably homogeneous on large scales, despite gigantic distances. Some theories try to explain this homogeneity via mechanisms linked to cosmic inflation. Others explore possible links with black hole geometries. But the most violent paradox appears when we combine quantum mechanics and the event horizon. In 2012, several physicists proposed a radical hypothesis: the quantum firewall. According to this theory, the event horizon would not be an empty boundary. It would be an ultra-energetic region capable of instantly destroying any incoming matter. A true quantum wall of fire. This idea arises because of a conflict between Hawking radiation, the conservation of information, and quantum entanglement. Quantum entanglement is a real phenomenon confirmed experimentally thousands of times. 2. Entangled particles remain instantaneously correlated, even when separated by great distances. But in certain calculations related to black holes, maintaining simultaneously entanglement, information conservation, and relativity becomes impossible. The firewall would then be a solution. But this solution directly destroys a fundamental principle of Einstein, the equivalence principle. According to general relativity, crossing the horizon of a supermassive black hole should produce no immediate, brutal local effect. The firewall says exactly the opposite. In other words, the two pillars of modern physics begin to come into direct conflict. And that is probably the most important point. Black holes are not simply extreme objects. They represent the precise place where our current understanding of the universe ceases to function properly. We now enter the zone where physics tries to piece things back together. Because at this stage, we have a simple problem. General relativity works perfectly for black holes on large scales. Quantum mechanics works perfectly for particles. But the two become incompatible exactly where black holes are the most extreme. And yet, black holes really exist in the universe. We have indirectly observed thousands of them. Notably, thanks to accretion disks and gravitational waves detected by instruments like LIGO and Virgo. For example, the merger of two black holes of several tens of solar masses releases an energy in the form of gravitational waves equivalent to several solar masses converted into pure energy in a fraction of a second. So nature knows how to handle these objects. But our theories are not yet unified. This is where a central idea of modern physics comes in: the holographic principle. The idea is surprising. All the information contained in a region of space could be described only by what happens on its surface. In other words, volume would be an illusion, and the real information would be stored on a two-dimensional surface. In the case of black holes, this surface is precisely the event horizon. This concept comes notably from the work of physicists like Gerard 't Hooft and Leonard Susskind. A famous equation even relates the maximum amount of information a black hole can contain to the surface area of its horizon, not its volume, which is totally counterintuitive. Because in our everyday experience, the larger an object is, the more information it contains in its volume. Here, it's the opposite. And this idea becomes even stronger with another formulation: the ADS/CFT correspondence, proposed by Juan Maldacena. In certain mathematical models, a gravitational universe in 3 dimensions can be entirely equivalent to a theory without gravity in 2 dimensions on its boundary. This means something radical. Gravity could be emergent. In other words, it would not be fundamental, but would arise from a deeper level of reality. And if that's true, black holes are not exceptions. They are windows onto that deeper structure. But one critical point remains: the information paradox. Today, the majority of physicists think that information is probably never destroyed. Even if it falls into a black hole, it would in reality be encoded in an extremely complex way on the event horizon, then gradually released via Hawking radiation, but not in direct form. In a highly chaotic, mixed, nearly undecipherable form, as if the universe encrypts information instead of erasing it. This point is important. It would allow preserving both quantum mechanics and relativity. But that implies something very strange. The interior of a black hole might never be directly accessible, even in theory. Not because it is too far away, but because the information needed to reconstruct it is already distributed elsewhere in the universe. And this is where physics reaches its current limits. Because all these theories remain unverified directly inside black holes. No probe can cross the horizon and come back. No information can come out intact. And so, part of reality remains fundamentally beyond experimental reach. Which naturally leads to the last scientific question. Is it a temporary problem? Or a structural limit of human knowledge? At this point, we leave pure physics and enter something more fundamental. Black holes pose a simple but brutal question. How far can human understanding of the universe go? Because there is a physical limit to observation. The speed of light, about 300,000 kilometers per second. The cosmological horizon, about 46 billion light-years for the observable universe. And black holes add another limit, a boundary where even the laws of information become ambiguous, which means that some regions of the universe are not just hard to observe, they are structurally inaccessible. And that changes everything. Because it means that science doesn't advance only because of a lack of technology. It also advances against fundamental physical limits. But paradoxically, it is precisely within these limits that the most important theories emerge. Black holes have already enabled the confirmation of gravitational waves, the indirect validation of general relativity under extreme conditions, and the direct tension between relativity and quantum mechanics. They are therefore both real astrophysical objects and extreme theoretical laboratories. And today, many physicists think they are the key to a unified theory. A theory capable of describing both the infinitely large, galaxies, universe, and the infinitely small, particles. What is often called the theory of everything. But there is an even deeper possibility. What if black holes were not just objects in the universe, but places where the universe itself changes regime? Zones where reality shifts from a classical description to a fully informational description. In this view, space, time, gravity would not be fundamental. They would be side effects, and black holes would be the places where this illusion becomes visible.
First of all, what is a black hole in astrophysics? A black hole is a celestial object so compact that the intensity of its gravitational field traps all forms of matter and radiation. Why the name black hole? Black holes are immensely dense. So dense, in fact, that they are not objects as such, but rather holes in the fabric of space. The inside of black holes is a mystery. What's more, black holes can neither emit nor scatter light. They are therefore black and optically invisible in our universe. Black holes are gigantic. Their dimensions are beyond comprehension. The largest black hole ever detected is said to be 66 billion times more massive than our Sun. The gravitational force of a black hole is such that nothing can escape. Black holes reign supreme over their environment, and perhaps over the entire universe. They attract matter, deflect light, and alter the course of time. Their gravity could slow down the hands of a clock. Black holes are the most extreme expression of the gravitational force. Nothing like the gravitational force we experience on Earth. We've never been able to get close to a black hole, and even if we had, we wouldn't have come back. But if we could get close to a black hole, what would we really see? Observing a black hole is impossible, but we can answer the question thanks to our theoretical models. Powerful and massive black holes exert effects on their surroundings. Observing these effects allows us not only to deduce the presence of a black hole, but also its properties. Einstein's theory of general relativity states that any object with mass curves space-time and bends the path of light. This is true of planets, galaxies, and galaxy clusters. It's also the case with black holes. To understand the effect of black holes on their environment, we need to borrow a concept from the field of optics, that of gravitational lensing. In optics, when we look at an image through a converging lens, it appears distorted, because the lens has the property of deflecting light. The same applies to the black hole. The black hole works like a gravitational lens. Like through a lens, light rays passing through a black hole are deflected from their original trajectory. The black hole is therefore a concentration of matter that deflects light. It modifies the path of light in its vicinity. But this is not the only clue that we are approaching a black hole. When the black hole absorbs the surrounding matter, it swirls in the same direction before being swallowed up by the black hole. A spiral is formed, known as the accretion disk. The material is heated to a very high temperature and emits a large quantity of X-rays. Visible to our instruments, the accretion disk reveals the presence of a black hole. We've detected a black hole, and now we're going to get closer to it. Theoretically, of course. The closer we get to the black hole, the more time seems to slow down. An observer on Earth might think we're moving slower and slower, but for us, everything's normal. From our vantage point, the Earth seems to be accelerating its rotation. We're now approaching the black hole's event horizon. The event horizon is the zone that delimits the region from which light and matter can no longer escape. This boundary is not visible. It's not a tangible boundary, but rather a point of no return. The closer we get to the black hole in the event horizon, the more an observer on Earth sees us slowing down, until we appear completely motionless. And yet, we still seem to be moving at the same speed. If this fictitious observer were to wait millions or billions of years, perhaps he would see us disappear forever, absorbed by the black hole. Nobody knows what's inside a black hole. Even if we did, we'd never be able to return to Earth to tell the story of what we'd seen. From the outside, the black hole looks completely black. But if we were inside, we'd be dazzled by all the light that's been absorbed into the black hole with us. This light is the last thing we'd see before being swallowed up forever in the black hole's extreme gravitational density. Once we'd crossed the event horizon, we'd fall towards the center of the black hole, where all its mass is concentrated. Our bodies would then begin to stretch like spaghetti, eventually disintegrating into elementary particles compressed into an infinitesimally small point. This is known as the singularity. Here, at the heart of the black hole, all our knowledge of space and time is called into question. And perhaps, who knows, at its heart the black hole is as vast as the universe? If black holes are invisible and we can't get close to them, how did we discover them? The existence of black holes has been predicted by theory for over 100 years. But it's only recently that we've detected the first direct evidence of the existence of black holes. On September 14, 2015, a powerful gravitational wave struck the Earth. Scientists at the LIGO Observatory recorded a tiny beep, an almost infinitesimal sound, but just detectable enough to make astrophysical history. For this signal comes from a very distant source. It has traveled over 1 billion light years to reach us. Where does this signal come from? research has revealed that it was caused by a collision, a massive collision, which would have generated a shock wave 50 times more powerful than all the energy produced by the visible universe. This gravitational wave then propagated through the universe at the speed of light, hitting galaxy after galaxy until it reached us. There is only one possible explanation for such a powerful shock wave: black holes. Theorizing about black holes has its origins in Newton's 17th century laws of physics. To understand black holes, we need to understand the notion of gravitation, formulated by Isaac Newton in 1687. Legend has it that the British mathematician, physicist, and astronomer understood the physical principle of gravitation while sitting under an apple tree when an apple fell on his head. Here's how he formulated this fundamental physical principle at the time. Any two bodies attract each other as a direct function of their mass and as an inverse function of the square of the distance between their centers of gravity. In other words, the apple is attracted to the Earth because its mass is greater. It falls towards the Earth's center of gravity at a speed that depends on its mass. Newton's laws were revolutionary. Until then, science had been able to describe natural physical phenomena, but not to calculate them. But while they explained the effects of gravity, they still didn't explain its nature. To understand the nature of gravity, we had to wait until the early 20th century and the principle of relativity explained by Albert Einstein. Einstein studied the motion of objects and wondered about the nature of gravity. To what does it do? A force or something else? Einstein was intrigued, for example, by the fact that an apple on a table could not be moved sideways without touching it. And yet, if we remove the table, the apple will move towards the floor, even though we haven't touched it. If we throw the apple, it will fall back in a curve. If we could throw it even harder, at a speed of 27,000 kilometers per hour, or 16,800 miles per hour, the trajectory described by the falling apple would be identical to the Earth's curvature. Einstein therefore theorized that the apple was falling freely along a trajectory made curved by the Earth. The Earth distorts space and time, just like the Sun and all other massed objects in the universe. Or, put another way, the mass of every object in the cosmos bends the space around it. According to Einstein's theory of general relativity, gravitation is not a force, but the manifestation of the curvature of space-time. The gravitation that causes the apple to fall is not a force exerted by the Earth on the apple, like a magnet, but the apple's reaction to the Earth's effect on space-time. A fundamental notion that would later lead to the theorization of black holes. The black hole hypothesis was first raised by astronomer Pierre-Simon de Laplace in the first edition of his book Exposition du Système du Monde in 1796. Black holes are then described as obscure bodies as considerable, and perhaps in as great a number as the stars. Laplace also explained that these dark bodies would exert a strong attraction, and would not let any of their light rays reach us. In other words, they would be invisible. This theory was subsequently removed from the third edition of 1808. Light was now perceived as a wave rather than a corpuscle. However, it was not yet clear how Newton's theory of gravitation could be linked to the phenomenon of waves. Invisible stars were therefore forgotten, until the First World War. While Einstein was publishing his theory of general relativity, another lesser-known scientist made his contribution to the theorization of black holes, the German astrophysicist Karl Schwarzschild. It was he who first established the link between gravitation and black holes. Even as a teenager, Carl Schwarzschild enjoyed calculating the intricate details of planetary orbits. No calculation, however complex, seemed to stop him. In 1916, he was mobilized to the Russian front. In the German army, he calculated the trajectories of artillery fire. At the same time, he continued his personal research. A few weeks after the publication of Einstein's work, he bought the book and immediately set about investigating the consequences of the new laws of gravitation for stars. In other words, he set out to calculate a star's gravitational field. Einstein came close, but only approximately. Carl Schwarzschild, on the other hand, calculated the exact solution to Einstein's equations. In just a few days, he calculated the curvature of space-time outside any non-rotating star. He sent a letter to Einstein with the results of his calculations. Einstein was flabbergasted and went to present the results to the Prussian Academy of Sciences. A few weeks later, he calculated the curvature of space-time inside the star and determined the minimum radius from which light could no longer escape. In the case of the Sun, he found it to be around 3 kilometers or 2 miles, in line with the results obtained by classical physics. A new feat that impressed Einstein. Carl Schwarzschild made a discovery that the genius himself had not anticipated. It is possible to calculate at what distance from a gravitational object a kind of boundary is established. The scientist concentrated the mass of a star in a single point, then calculated how this mass would bend space and deflect light rays passing nearby. He then directs particles of light or matter towards this point and finds that a boundary stops the particles. This is the event horizon, the famous boundary that delimits the no-return zone of black holes. Anything that enters this zone is trapped. In a word, it's a hole in space-time. Any mass compressed into a sufficiently small space creates this hole in space-time, now known as a black hole. This idea didn't appeal to Einstein, who refused to believe in the existence of black holes. Unfortunately, Carl Schwarzschild was unable to develop his theory any further. He died in June 1916 of an illness contracted on the Russian front. By the end of the war, his theory seemed doomed to oblivion. Over the following decades, physicists were to unlock the secrets of the atom and discover nuclear fusion. A discovery that reignited the debate with the theorization of stellar black holes. Over the course of the 20th century, research progressed on stars and the mechanisms that govern their life cycles. Like us, stars have a life cycle. They are born, develop, and die. Stars are born in nebulae, clouds of dust and gas. Under certain conditions, nebulae can collapse in on themselves. Gravitational contraction heats up matter. When this matter reaches a certain temperature, nuclear fusion begins. The protostar contracts, gets hotter and hotter, and begins to glow intensely. 100,000 years later, it reaches its maximum luminosity. Gravitational collapse continues, and the star diminishes in size and luminosity. After a few tens of millions of years, the star joins the main sequence. All stars, whatever their mass, begin to burn hydrogen, the lightest atom. The fusion of hydrogen atoms produces helium, then heavier elements. The force of gravity seeks to crush the star's mass, but the amount of energy released outwards by fusion prevents the star from collapsing. A mature star is relatively stable. It lives for around 10 billion years in the main series. The helium formed by hydrogen fusion accumulates in its core, When the hydrogen is exhausted, the star becomes a red giant. It expands and the outer layers cool. Once the red giant's core has cooled, the remaining gases float away, forming a planetary nebula. At the heart of this planetary nebula remains the star's core, small, dense, and hot. The star is then called a white dwarf. After a while, the star's core cools completely and stops glowing. This is the black dwarf. By studying the life cycle of stars, scientists like Oppenheimer discovered that the most massive stars die differently from the smallest ones. They discovered that a star's life cycle depended on its mass. Mass determines what the star will become when it has burned up all its hydrogen. Small stars cannot fuse elements heavier than helium. On the other hand, the most massive stars can continue their fusion to form heavier and heavier elements, such as iron. Large stars form supernovas. The star's core is very massive. Nothing can stop the gravitational force. No force can prevent the star's core from collapsing. Theoretically, this gravitational force will then compress the star's mass into an infinitely small point, the black hole. 50 years after Carl Schwarzschild's theoretical discovery of black holes, scientists have identified the mechanism that could be at the origin of black hole formation: the death of a massive star, or supernova. But many physicists remain skeptical, including Einstein. This gave rise to a debate between the proponents of black holes and those who didn't believe in them. American physicist John Wheeler is one of the proponents of the existence of black holes. He worked extensively on gravitational collapse theory and later became a pioneer in the field of quantum gravity. In 1967, he was the first to use the term black hole in a lecture at NASA's Goddard Institute for Space Studies. Although black holes had been predicted by theoretical models since the early 20th century, it wasn't until the 1960s that the first concrete proof of their existence was obtained. At the time, astrophysicists were faced with a real challenge. How could they detect a black hole when they couldn't see it? How can we see the invisible? Theory tells us that our galaxy is studded with small stellar black holes, the corpses of massive stars at least 10 times the mass of the Sun. These small black holes are invisible, but we can study them by analyzing the effects they exert on their surroundings. It's like walking around a stadium. You can't see what's going on, but you can tell if there's a match going on by looking outside the stadium. The crowds, the noise, the fans. What effects does a black hole have on its environment? What must we look for to detect its presence? To understand this, we need to go back in time. The year is 1932. American physicist Carl Jansky, a radio engineer at Bell Laboratory, detects mysterious radio waves coming from the farthest reaches of our galaxy, the Milky Way. Our galaxy emits radio waves. A surprising discovery that marked the birth of radio astronomy. 30 years later, in June 1962, a team of American researchers, led by Roberto Giacconi, made another discovery that would revolutionize our conception of the heavens. While attempting to measure the sun's X-rays reflected by the moon's surface, Roberto Giacconi picked up a strong burst of X-rays coming from the Scorpio constellation, in the direction of the center of the Milky Way. This X-ray source was christened Scorpius X1. It will long remain an enigma for astrophysicists. It is 10,000 times brighter in X-rays than in the visible range, and the energy it gives off is 100,000 times greater than the Sun's total radiative emission in all wavelengths. Thanks to this discovery, Riccardo Giacconi was awarded the Nobel Prize in Physics in 2002. Radio astronomy revolutionized the hunt for black holes. It was later discovered that the X-rays in the universe actually come from very dense exotic stars, white dwarfs, neutron stars, or black holes. But what exactly is radio astronomy? Our eyes perceive only a very narrow portion of the electromagnetic spectrum. If we were to unroll it across the Brooklyn Bridge, the visible portion would measure just 1 meter across the bridge's 1,834 meters, or 6,017 feet. There are several types of waves with very different frequencies: radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. Radio astronomy is the study of X-rays, the most energetic part of the spectrum. Since its beginnings in the 1930s, it has enabled us to detect invisible objects emitting previously unsuspected high energies. Before these discoveries, the Milky Way seemed rather quiet, but it turns out to be rather chaotic. Following these discoveries, astrophysicists set out to find out where all this energy was coming from. At the end of the 20th century, here's what was known about X-ray sources. They are invisible to ordinary optical telescopes. They are very hot, with temperatures that can reach tens of millions of degrees Celsius. One of the first X-ray sources to attract astronomers' attention was named Cygnus X1. It was the first candidate for the title of black hole. In the early 1970s, British astronomer Paul Merton was offered a research post at the Royal Observatory, Greenwich. He was offered a 3-year contract. His objective: to discover the origins of the powerful cosmic X-ray sources recently detected, in particular, Cygnus X1, discovered in 1964. After exploring a few unsuccessful leads, he and his colleague Louise Webster decided to investigate whether the source came from a binary star. His hypothesis: there are binary stars, one of which is visible, while the other is invisible and emits X-rays. Binary stars orbit each other, so we need to look for a star in the area where Cygnus X1 was detected that shows signs of orbital motion. To do this, they rely on the Doppler effect. As a star moves closer to us, its light appears bluer, as its wavelength decreases. As it moves further away, it appears redder, as its wavelength increases. So they looked for color variations. The two researchers soon discovered that the star, HDE 226868, orbits an invisible partner in 5.6 days, which could be the X-ray source Cygnus X1. This discovery enables them to estimate the mass of Cygnus X1, which would be at least 2.5 solar masses, and certainly more than 6 solar masses. This invisible partner has sufficient mass and gravity to drive the rotation of the star HDE 226868. But it emits no luminosity. Such a star cannot be a white dwarf or a neutron star. There's only one explanation: it's a black hole. But this was the 1970s, and many researchers were still skeptical about the notion of a black hole. In September 1971, Paul Merton and Louise Webster submitted an article on this discovery to the journal Nature, where the term black hole was only mentioned at the very end of the article. We thought it might be a black hole. Other astronomers are equally convinced that this is the first black hole observed, but we still lack proof. In December 1974, physicists Kip Thorne and Stephen Hawking made a bet. Kip Thorne bets that Cygnus X1 is a black hole. Stephen Hawking, although convinced that it is a black hole, chooses to bet the opposite out of superstition. Gradually, the arguments in favor of a black hole multiplied. In June 1990, Stephen Hawking conceded defeat. The accumulated evidence was enough to end the debate between the two scientists, but not enough to convince the skeptics and become an authority. Among other things, Paul Merton's calculation of the mass of Cygnus X1 was considered too approximate. 20 years later, American astronomer Mark Reed of the Smithsonian Astrophysical Observatory set out to prove once and for all that Cygnus X1 was indeed a stellar black hole, and the first ever identified. To do so, he had to calculate its exact mass. A real challenge since Cygnus X1 is invisible. To do this, he used Kepler's laws, which allow us to calculate the mass of a celestial object from its distance. So, he starts by measuring the distance to Cygnus X1. He uses the concept of parallax. To understand the concept of parallax, you'll need to do a little experiment. Take an object in your hand, a pen, a glass of water, your cell phone. Move the object away from you until it's at arm's length. Close your right eye and look at the object with your left. Then close your left eye and look at it with your right. You get the impression that it has changed position, while the background has remained motionless. It's an optical effect that allows our eyes and brains to see in 3D. In astronomy, parallax is the periodic shift in the apparent positions of nearby stars due to the Earth's variable position in its orbit around the Sun. In other words, if you look at a nearby star in the sky tonight, such as Sirius, and then look at it again 6 months later, it will appear to have moved, while the other, more distant stars have not. The closer the star, the more likely it is to have moved. When astronomers use parallax, they obtain a triangle formed by 3 points: the observed object and the Earth at 2 different locations. Mark Reed has used this concept to measure the distance to Cygnus X1. We already know the measure of the base of the triangle, as it is equivalent to the Earth's orbit. The rules of trigonometry then allow us to calculate the angle of the triangle, then the other sides, and thus the distance separating us from Cygnus X1. But this X-ray source is so far away that the angle is infinitesimal. To measure such a small angle, Mark Reed and his team had to simultaneously use 10 radio telescopes to reproduce the equivalent of a telescope with the same diameter as the Earth. Thanks to these calculations, Mark Reed was able to precisely measure not only the distance separating us from this binary system, but also the black hole's mass, rotation speed, and speed of travel in our galaxy. In 2011, the astronomer and his team determined that Cygnus X1 is 6,000 light-years away. Its mass was then estimated at 15 times that of the Sun. It could only be a black hole. Later, Cygnus X1's mass was re-estimated at 21 times that of the Sun. 40 years after being identified as a potential candidate for the title of first stellar black hole discovered, Cygnus X1 was confirmed to be a black hole. After years of speculation, science has finally proven the existence of these mysterious cosmic objects. What would we see if we approached Cygnus X1? Like all stellar black holes, Cygnus X1 is surrounded by an accretion disk. Its event horizon is masked by a cloud of gas and dust that swirls around at dizzying speed. The more gravity pulls matter towards the black hole, the faster this disk swirls. the accretion disk acts like a particle gas pedal. Particles whirl faster and faster, reaching half the speed of light. They collide and heat up to several million degrees. At such temperatures, the particles emit X-rays. Another special feature of Cygnus X1 is its companion star. This is a super blue giant, which orbits the black hole in 5.6 days. Its orbit is so close to Cygnus X1 that it pulls matter from it, which gradually joins the accretion disk. Part of the star crosses the event horizon and is swallowed up by the black hole forever. We can also observe enormous jets of matter. These are particles ejected at high speed from the north and south poles of the black hole, perpendicular to the accretion disk. We still don't know exactly what mechanisms govern the jets of matter from black holes. What we do know is that these jets are highly concentrated and very powerful. They propagate far into space at close to the speed of light. They generate magnetic fields. Cygnus X1 is a veritable fireball, very active and very violent. No wonder astrophysicists have long found it hard to believe in the existence of such extreme objects. There's no longer any doubt. Cygnus X1 is the result of the supernova explosion of a massive star, over 40 solar masses and no more than 5 million years old. No law of physics can describe an object of 21 solar masses contained in a diameter of 100 kilometers without concluding that it is a black hole. But a new discovery once again shook astrophysicists' certainties about the stellar origin of black holes: the discovery of quasars. The first quasar was discovered in 1962 by Martin Schmidt. This mysterious hotspot emitting radio radiation was named 3C273. This source of quasi-stellar radiation was dubbed a quasar. Astrophysicists immediately wondered whether this object was a new type of star. Quasars look like stars, but could they be totally different objects in the cosmos? To find out, researchers are analyzing their electromagnetic radiation. In the case of a star, we can analyze its electromagnetic radiation to deduce its chemical composition. This is what astrophysicists tried to do with a quasar, but they were faced with an incomprehensible light spectrum. It was as if all the emissions came from unknown elements. In 1963, Martin Schmidt finally identified the imprint of a known element in the quasar's spectrum: hydrogen. This imprint is not where you'd expect it to be, which explains why it hadn't been detected before. The hydrogen lines are redshifted, so much so that the hydrogen is unrecognizable. What does this mean? This shift means that the quasar observed is moving away from us at dizzying speed. Astronomers have never seen such an extreme light shift. The distance between quasars can be explained by the expansion of the universe. But we have yet to explain where all the quasar's energy comes from. According to calculations, such energy cannot come from a chemical or nuclear reaction. The quasar cannot be a molten star, as stellar fusion is incapable of producing such energy. The only possible engine is gravitation, concentrated to the extreme, as in a black hole. Researchers began to wonder. A hypothesis took shape. The energy emitted by quasars would draw its power from the accretion disks of black holes. But to produce so much energy, a black hole would have to be much more massive than the stellar black holes identified to date. Cygnus X1 contains just 20 solar masses. To explain the quasar, we'd need a black hole millions or billions of times more massive than the Sun. The black holes that fuel quasars are in a completely different category, even more unimaginable than stellar black holes. These are supermassive black holes. Although this hypothesis seemed incredible at the time, it is now widely accepted by the scientific community. We now know that a quasar is a disk of hot gas spinning very rapidly around a supermassive black hole. The brightest quasar ever detected, J0529-4351, comes from a black hole containing more than 17 billion times the mass of our Sun. The first supermassive black hole to be discovered and identified as such is the one at the center of our galaxy, Sagittarius A. The center of our galaxy lies in the direction of the Sagittarius constellation. We can't observe it directly. Stars, dust, and gas block our view. If we were an intergalactic traveler and could observe our galaxy from the outside, what would we see? Let's step outside our galaxy for a moment and admire it from the outside. You're looking at a magnificent, slowly spinning spiral galaxy about 100,000 light-years across. As you can see, this spiral is relatively thin, only 1,000 light-years thick. Look closely. This is where our solar system is located, 26,000 light-years from the center of the Milky Way. The galaxy's core is very dense, with millions of stars and lots of dust and gas. When we look towards the center of the galaxy from Earth, we see a white band. This part of the galaxy obstructs our view. How was it possible to detect a black hole in the midst of all these stars, gas, and dust? To understand this, we need to jump back in time. The year is 1933. Carl Jansky, the father of radio astronomy, discovered an intense radio signal coming from the center of the Milky Way in the constellation Sagittarius. Assigned to another project, he had no time to develop his discovery. He would have to wait more than 40 years to find out more. In February 1974, the origin of this signal was clearly identified at the Green Bank Observatory in the USA as coming from the Sagittarius A radio source. It would be even later, in the 1990s, that a supermassive black hole would be discovered at the center of our galaxy and associated with this radio source. The researchers behind this discovery, Reinhard Genzel, Roger Penrose, and Andrea M. Ghez, were awarded the Nobel Prize in 2020. The 1990s saw the emergence of the idea that many massive galaxies host a black hole at their center. By confirming and identifying a supermassive black hole at the center of our galaxy remains a real challenge. Not only because of the many stars that impede observation, but also because our instruments come up against a major problem: atmospheric distortion. Researchers set out to follow the course of individual stars orbiting the center of the galaxy. But the constant variations in the atmosphere deflect the light like a distorting mirror, making it more difficult to observe these stars. To correct this, astrophysicists are using an advanced military technique, which will enable them to obtain the sharpest images of the galaxy's center ever obtained. Finally, it is possible to distinguish each individual star near the center. In 1995, sky surveys began. Every year, astronomers take a photo of this region of the sky. After a few years, a frame-by-frame video of the stellar orbits of the stars studied was obtained. Analysis of these records reveals some breathtaking discoveries. Stars orbit the center of the Milky Way at dizzying speeds, up to 36 million kilometers per hour, or 22 million miles per hour. To explain this, they must orbit a very massive object, 4 million solar masses in size, but also invisible. At last, we have proof that there is indeed a silent, inactive supermassive black hole at the center of the galaxy. As before, it was the effects of the black hole on its surroundings that enabled researchers to identify it. Above all, this discovery marks the most convincing evidence of a completely new category of black hole hitherto unsuspected: supermassive black holes. In the middle of our galaxy lies a supermassive black hole, 4 million times the mass of the Sun. Could it be the same in other galaxies? A question that fascinates astrophysicists. But how does one go about identifying black holes at the center of distant galaxies? To find out whether a supermassive black hole is sitting at the center of a galaxy, we need to determine how fast the stars in that galaxy are moving. This is what we did to find Sagittarius A. But the problem is that the other galaxies are too far away for us to be able to measure individual star speeds as we did for the Milky Way. To get around this problem, astrophysicists have used the Hubble telescope. The idea is to take a photo of the galaxy observed with Hubble. This photo shows the distribution of stars in the galaxy and how it is structured. Next, the variations in light from blue to red are analyzed to deduce the average speed at which the stars orbit the galaxy's center. The next step is more tedious. The researchers recreate a computer replica of the galaxy using the data collected. Each model built must take into account not only the mass distribution of the stars, but also their motion. Methodically, for each galaxy observed, the researchers build a model and adjust the mass and velocity parameters until the model coincides with the observations made by Hubble. This method was developed by Princeton astronomer Martin Schwarzschild. For the record, Martin Schwarzschild is none other than the son of Karl Schwarzschild, the man who first theorized the existence of black holes from the Russian front. This method requires a great deal of patience and thousands of trials before arriving at a faithful model. What researchers have noticed is that without a black hole at the center, no matter how many combinations are tried, the models will never coincide. Of the 30 galaxies studied, it appears that almost all have a supermassive black hole at their center. A staggering discovery that exceeds astronomers' expectations. There are supermassive black holes at the center of all major galaxies, not just the Milky Way. To find out more, we're going to take a closer look at the Andromeda Galaxy, or M31, a galaxy relatively close to us, 2.5 million light-years from Earth. It's one of the few galaxies observable to the naked eye from Earth, particularly from the northern hemisphere. Astronomers suspect that it conceals a supermassive black hole. As with the Milky Way, when we look at the center of the Andromeda Galaxy, we see only a very dense cluster of stars, gas, and dust. That's enough to put us on the right track. It is likely that there is a supermassive black hole at the center of the Andromeda Galaxy. Today, this black hole would be relatively quiet. A few billion years ago, it may have been smaller, surrounded by gas, stars, and other smaller stellar black holes. It may have fed a quasar and begun to nibble away at its surroundings, absorbing all the nearest gas and stars within a few 100 million years. It is now so colossal that if deposited at the center of our solar system, it would swallow up Mercury, Venus, Earth, and Mars. Jupiter and Saturn, meanwhile, would be inexorably drawn into its gravitational field. The mass of this colossal black hole is estimated at over 100 million times that of the Sun. Its rotation is extremely rapid. The accretion disk that surrounds it rotates at half the speed of light, a veritable cosmic tornado. If Jupiter rotated that fast, its orbit around the Sun would last just a few hours instead of 11.86 years. If we were swept up in the vortex surrounding the gigantic black hole in the Andromeda Galaxy, we'd end up seeing each other from behind, with light forever trapped in this circle. A monstrous, disproportionate object that theory had never anticipated. Supermassive black holes, unlike stellar black holes, were not predicted by science. They were first observed. Their size, mass, and properties are beyond comprehension. Further observations in other galaxies have added further knots to the problem. In June 2004, astronomers found a supermassive black hole, Q0906 plus 6930, at the center of a distant galaxy. Q0906 plus 6930 is a blazar, a very compact quasar associated with a supermassive black hole. At the time, it was the most distant ever detected. It has a redshift of 5.47, meaning it is 12.3 billion light-years away. The discovery of this distant black hole has added a new layer to the mystery of supermassive black holes. When we look at this black hole, we are looking back 12.3 billion years when the universe was very young. This means that the formation of supermassive black holes goes back to the very beginnings of the universe, and that this process is not as long as we might think. In 2022, scientists from the Event Horizon Telescope succeeded in photographing Sagittarius A, the supermassive black hole that sits in the middle of our galaxy. The image reconstructed from the data collected is blurred and imprecise, but it is nonetheless historic. It is the first pictorial proof of a black hole for which there were previously only hints. It took EHT's 300 scientists no less than 4 years to analyze data collected in 2017 and produce this image. In this image, we can't see the black hole, which is invisible. The orange halo we see is the superheated matter in the black hole's accretion disk, which emits radio waves. The Event Horizon Telescope is a network of 8 radio telescopes on 4 continents. Working together, these 8 radio telescopes form a telescope with a diameter equivalent to that of the Earth. By meticulously recombining the millimeter wave signals from each telescope, scientists have been able to obtain a faithful image of the black hole sitting at the center of our galaxy. Impressive and historic as it is, this photo of Sagittarius A was not the first image of a black hole to be unveiled. In 2019, the EHT team had already published an image of a black hole located in a galaxy close to our own, M87. This black hole, called M87, was the first to be photographed. M87 is located 55 million light-years from Earth. It is therefore further away than Sagittarius A. But its black hole is also much more massive, and therefore easier to photograph. M87 is 1,600 times more massive than Sagittarius A, or 4 million times more massive than the Sun. How did we get an image of this supermassive black hole, located over 50 million light-years away? Our telescopes have long been focused on M87, a giant elliptical galaxy discovered in 1781. And with good reason. Not only is it the largest elliptical galaxy closest to Earth, it's also one of the brightest radio sources in the sky. As early as 1918, astronomer Albert Curtis observed a strange phenomenon, later understood to be a jet of matter from the accretion disk of the black hole at the galaxy's center. This jet of matter extends over at least 5,000 light-years. To study this strange phenomenon, NASA used its Chandra satellite. Between 2012 and 2017, Chandra studied this jet of matter in the X-ray range. Scientists were able to obtain an estimate of the velocity of two concentrations of matter in this jet. And the result exceeded all expectations. The observed concentrations of matter are moving faster than light, 6.3 times faster for one and 2.4 times for the other. These results sent shockwaves through the scientific community. According to Einstein's theory of relativity, a signal cannot travel faster than light. In fact, it turned out to be an optical illusion. The particles that make up the concentrations of matter studied are actually moving at 99% the speed of light. A surprising result, since this is the first time such a high speed has been measured. M87 had already caused quite a stir. What enabled us to photograph it in 2019 was its high luminosity. Black holes emit no light. They are invisible. But the concentrations of matter that surround them can be very luminous, at least in the X-ray range. We have never yet been able to observe a black hole in the visible range. By observing M87, astrophysicists raised another problem. If this supermassive black hole had been created by the collapse of a massive star, or supernova, its intense radiation should only have lasted a few months. However, M87 has been emitting X-rays for much longer than that. We know that an active black hole that feeds on matter emits X-rays. Could M87 be a black hole devouring a massive object? Possibly. But this would be a far more significant phenomenon than the slow nibbling of nearby stars by the stellar black hole Cygnus X1. Any star passing too close to M87 would be swallowed up in just 10 years, which is very short time on a cosmic scale. This is known as tidal destruction. The tidal effect being, of course, billions of times more intense and destructive than the one that creates our tides on Earth. We now have both theoretical and visual proof that supermassive black holes exist. But these powerful objects, whose very nature boggles the mind, have yet to reveal all their secrets. Cygnus X1 measures 21 solar masses, Sagittarius A 4 million solar masses, and the black hole in the Andromeda Galaxy 100 million solar masses. And it's not the most massive. Today, black holes of phenomenal dimensions have been discovered, up to 66 billion times the mass of the Sun. How is such an order of magnitude possible? How can supermassive black holes grow so large? If stellar black holes are the remnants of dead stars, what are supermassive black holes? They are unlikely to have arisen from the collapse of a star. No star is tens of billions of times more massive than the Sun. Astrophysicists, bewildered by the gigantic dimensions of supermassive black holes, have been investigating the mechanism behind the formation of these monstrous objects. Supermassive black holes may develop through gas accretion. Gas gathers and rapidly forms an accretion disk, made up of several elements in gaseous form. These gases swirl around, approaching the event horizon and causing the black hole to expand. Matter in the vicinity of the black hole is also inexorably drawn in by the black hole's unprecedented gravity. It joins the vortex and adds to the mass of the black hole. But there must be more to it than that. Why else would supermassive black holes grow so fast? This is a paradox. Quasars are the ancestors of supermassive black holes. These objects are visible to our instruments because they are so luminous, but we mustn't forget that they are very distant from us and therefore very old. Ever since their discovery in the 1960s, quasars have raised a number of paradoxes. The strangest is that they are ultra-bright in a still very young, predominantly dark universe. They emit so much energy that they must contain a supermassive black hole at their center. And yet, they belong to the primordial universe. In other words, very early in the history of the universe, just 600 million years after the Big Bang, titanic objects of several billion solar masses were observed. This observation poses a problem, and nothing in our current physical knowledge seems able to explain it. How did these black holes become so huge so quickly? This paradox touches the very limits of physics. For there is what is known as the Eddington limit. According to English astrophysicist Arthur Stanley Eddington, mature stars are stable thanks to radiation pressure, not hydrostatic pressure. It is this pressure that keeps the star in equilibrium despite its gravity, which pushes it to collapse. In the case of a massive star, the energy produced is so great that the blast of light causes the star to lose mass. The Eddington limit corresponds to the maximum luminosity that a massive star can reach, as a function of its mass without vaporizing itself. By extension, the accretion mechanism of a black hole cannot exceed a certain speed. In other words, the light ejected by the disk prevents the black hole from feeding too quickly. The light exerts pressure, pushing the gas away, and beyond a certain limit, it would slow down the black hole's growth. This limit makes the very concept of the quasar even more paradoxical. How did quasars acquire such mass so quickly? Is it possible to circumvent the Eddington limit? Surely there must be some process by which black holes that are already supermassive can be created as soon as they are born. All we can do at present is speculate. One of the most plausible hypotheses is the direct collapse theory, developed by Canadian researchers. This hypothesis implies that a gas cloud could directly generate a black hole. Black holes would form over a very short period of time, then suddenly stop growing. Let's see how this could happen. It all starts with clouds of gas made up of elements such as hydrogen and helium, which are needed to make a star. As in the process of creating a star, the densest clouds will collapse in on themselves. But not all areas of the cloud collapse at the same speed, causing the gas cloud to fragment. These fragments collapse until the hydrogen atoms come together. Nuclear fusion begins and stars are born. But what happens if the giant cloud collapses without creating stars? Under certain precise conditions, it's possible for a large gaseous disk to form before stars are born. This disk becomes unstable. Its mass is propelled rapidly towards the center, and a very massive black hole is formed. It's the same phenomenon as tornadoes, but on a much more massive scale. To understand this phenomenon, you can also imagine what happens when you take a bath and pull the plug out of the tub. A mini tornado forms. This theory of direct collapse could explain many things. Direct collapse would have enabled the primordial universe to create gigantic black holes from clouds of gas, without going through the star creation phase. As a result, black holes were already massive when they were born, enabling them to grow very rapidly. According to this theory, black holes with a mass 10,000 to 100,000 times that of the Sun could have been born, giving them a considerable head start. With such mass and gravitational influence, supermassive black holes are bound to play a role in the organization of the cosmos and the structure of the universe. At least that's the question astrophysicists have been asking themselves. It would seem logical. Supermassive black holes are never alone. They are inseparable from galaxies. At the heart of every massive galaxy lies a supermassive black hole. The larger the galaxy, the more massive the black hole. These observations raise several questions. Is there a symbiotic relationship between a galaxy and the black hole it contains? Are black holes indispensable to galaxies? Which came first, the galaxy or the black hole? Did they develop simultaneously? Astrophysicists believe that the process that gave birth to one also created the other. The black hole and the galaxy feed off each other. What impact does the black hole have on its host galaxy? What we do know is that galaxies grow by creating new stars from clouds of hydrogen. When all the gas is used up, there can be no more new stars. We also know that when a black hole swallows matter, it releases a phenomenal amount of energy back into the galaxy. This energy heats up the gases. Gas that is too hot can no longer form stars. The heat generated by a growing black hole therefore also prevents the formation of new stars, at least in the vicinity of the black hole. It therefore appears that a black hole influences the evolution of its host galaxy by slowing down star formation. The galaxy will either stagnate or expand, depending on the growth of the black hole. It would seem then that black holes do indeed control the architecture of the universe, not through their size, as once thought, but through the way the energy they emit shapes galaxies. In 2019, researchers at the University of California at Riverside proved that supermassive black holes can disrupt star formation in dwarf galaxies. Dwarf galaxies have between 100 million and a few billion stars, which is small compared to the 400 billion stars the Milky Way could contain. Supermassive black holes can be found at the center of dwarf galaxies, although this is rare. Supermassive black holes create powerful winds, which have a direct influence on the rate of star formation in the dwarf galaxy. In 2023, French astrophysicist David Elbaz and his team complemented these findings with a new study published in the journal Nature. The researchers showed that even at the heart of large galaxies, supermassive black holes emit winds of matter that disrupt the host galaxy's reservoirs of cold gas. In the end, the blast of black holes expels the cold gas capable of forming new stars from large galaxies. It is therefore the mass of the central black hole, rather than the mass of the galaxy, that determines the amount of gas present in galaxies. The role of black holes on the scale of the entire universe would be phenomenal. If we were to add up all the black holes in the universe, they would amount to nothing. And yet, their energy is such that they control the distribution of gas and matter in galaxies. In the last 10 years, new discoveries have been made about black holes and have provided some answers to questions we've been asking, particularly about the formation processes of supermassive black holes. On September 14, 2015, astrophysicists at the LIGO Observatory detected for the first time the gravitational waves emitted by the merger of two black holes. This discovery earned them the Nobel Prize in 2017. It proved that black holes can merge and thus gain mass very rapidly. We now know that many stellar black holes meet and merge to form larger black holes. 2 years after the discovery of black hole mergers in August 2017, LIGO once again detected an unprecedented event. This time, researchers are detecting gravitational waves generated by the collision of two neutron stars within the galaxy NGC 4993. Neutron stars are very dense, dead stars that can collide and light up the sky. A collision so powerful that it may have given rise to a black hole. The launch of the James Webb Telescope in December 2021 has revolutionized black hole research. This new telescope can see into the infrared even further than its predecessors. It can explore very old galaxies and will surely reveal much about their role in the formation of primitive galaxies. 2024 was a fruitful year for black hole research. An observation by James Webb revealed two supermassive black holes 2,000 light-years apart, about to merge. Measurements taken by the Space Telescope show that within 100 million years these two black holes will merge. One of these two black holes has a mass 50 million times that of the Sun, which is enormous compared to the 4 million solar masses of Sagittarius A. This discovery is unprecedented for the scientific community. In the same year, we witnessed for the first time the awakening of a black hole some 300 million light-years away. Astrophysicists saw it activate live. Suddenly, the previously rather quiet black hole became very bright, swallowing and heating up the gas around it. A stroke of luck? Above all, a feat made possible by the world's largest telescopes, the Keck in Hawaii and the Very Large Telescope in Chile. Another important discovery. Australian astrophysicist Daniel Price has published his work on what is known as a tidal disruption event, TDE. Theorized since the 1970s, this event occurs when a star gets too close to a supermassive black hole. Its tidal forces will compress the star to the point of producing a major deformation, known as a stellar pancake. This is also known as spaghettification. Theoretically, the star eventually explodes and its debris is swallowed up by the black hole. For over a year, Daniel Price's team carried out computer simulations to understand this phenomenon. The models reveal that instead of an accretion disk, the equivalent of a star's envelope forms around the black hole during a TDE. In other words, a sun black hole. A fascinating notion to be explored in the coming years. Although black hole research has made great strides in recent years, many questions will remain unanswered unless we can observe the formation of a black hole live. We will never know where black holes come from, what they contain beyond the event horizon, or what their past is. But we can, thanks to our observations and the models that have emerged from them, imagine the future of the universe and the influence that black holes will have on its movements. We can imagine that black holes will only increase in number and size. Perhaps one day, billions of years from now, all the matter in the universe will be swallowed up. Perhaps black holes themselves will disappear forever, giving way to a whole new reality.
Let's begin our exploration with a discovery that is one step closer to finding a habitable world beyond our solar system. On September 12, 2023, NASA reported that the James Webb had found gas showing the presence of an ocean on a planet 120 light-years from Earth, the planet K2-18b. The telescope found traces of molecules such as carbon, methane, and carbon dioxide, which could indicate that this exoplanet is covered by an ocean, with a hydrogen-rich atmosphere. K2-18b would therefore be a high-oceanic planet, i.e. an ocean planet with a predominantly hydrogen atmosphere. In fact, Hubble had already found traces of water vapor in this planet's atmosphere, but the James Webb observations once again confirm scientists' suspicions. The James Webb also discovered a molecule called dimethyl sulfide, or DMS. This molecule is only produced on Earth by life, notably phytoplankton. On K2-18b, there may therefore be the equivalent of terrestrial phytoplankton. This discovery is therefore very promising and could be a clue to life on a planet in the near universe. All the more so as K2-18b is located in its star's habitable zone. NASA remains cautious and has made it clear that further checks are required to confirm the presence of an ocean on this planet. In any case, the information gathered by the James Webb is best interpreted by this hypothesis of an ocean on the planet's surface. The most widely accepted hypothesis at present is that, like Neptune, K2-18b harbors a vast high-pressure ice mantle with a surface ocean and a thinner, hydrogen-rich atmosphere. The ocean, however, would be too hot to be liquid or habitable. Confirming this hypothesis will be complicated, even with the prowess of the James Webb. Indeed, the brightness of this exoplanet's parent star is so low that when the planet transits in front of it, only a tiny fraction of the light reaches the telescope. However, just 2 observations have yielded a wealth of interesting data, and further observations are in progress. So it's a safe bet that we'll soon have new information about this planet. On the other hand, some scientists remain skeptical about the concept of a high oceanic planet. Admittedly, models and simulations show us that they could very well exist. But the existence of water in liquid form is subject to very precise parameters with very small windows, and all it takes is for one of them to move just a little for water to no longer exist in liquid form. For example, a certain level of hydrogen in the atmosphere of an exoplanet can guarantee water in liquid form on its surface, but if there's just a little too much hydrogen in the atmosphere, the water no longer exists in liquid form, but in supercritical form. Or, as on Earth, mechanisms would have to exist to stabilize the conditions that make it possible for water to exist in its liquid state. However, it is unlikely that all oceanic planets possess the same plate tectonics and volcanism mechanisms as Earth. All we can do now is wait for further data from James Webb to find out more about this exoplanet and about oceanic planets in general. Let's move on to another James Webb discovery. Take a look at this image. It was taken by the James Webb on August 31, 2023. You can see supernova 1987A, or SN 1987A, one of the best-known supernovae. Located 168,000 light-years away in the Large Magellanic Cloud, it has been observed for almost 40 years. Why, if it's already known, has this supernova been observed again with the James Webb? What did astronomers expect to discover? Quite simply, because astronomers hope to use it to understand how a supernova develops over time. To better understand James Webb's recent discoveries, let's take a look back at the story of this supernova's discovery. As its name suggests, SN 1987A was discovered in 1987, in the month of February. The discovery was made by Chilean astronomers Ian Shelton and Oscar Duhalde. It is a Type II supernova, i.e. the result of the gravitational collapse of a massive stellar core that has exhausted its nuclear fuel. Let's keep it simple. Originally, there was a star called Sandalik 69202, a blue supergiant born 10 million years ago from a stellar collision with fusion. This star had a mass 20 times that of our Sun. When the star ran out of fuel, it was unable to maintain a balance between the gravitational forces and the pressure forces generated by nuclear fusion. Eventually, it exploded, releasing a large amount of light and matter into space, resulting in a Type II supernova. SN 1987A was the first supernova to be observed with the naked eye since the dawn of modern astronomy. Since its discovery, telescopes around the world have observed this supernova, including NASA's Chandra X-ray Observatory, which has examined it repeatedly during 17 years of scientific operations. Between 1999 and 2013, Chandra's data showed an expanding ring of X-ray emission that grew brighter and brighter, certainly produced by the shock wave from the supernova's explosion. Hubble had also observed this supernova, so it made sense to continue observations with James Webb. The photograph taken by the James Webb Telescope has enabled scientists to advance their understanding of this supernova. At the center of the supernova, you can see a keyhole formed by the matter ejected from the supernova, namely gas and dust. A structure that has never been observed before. To the left and right of this keyhole structure, you can also see crescents, shapes recently discovered by the James Webb. Beyond the center of the supernova, you can see an equatorial ring of material ejected tens of thousands of years before the supernova exploded. This equatorial ring contains bright hot spots that formed when the shock wave from the explosion caught up and heated the material in the ring. Around the equatorial ring, you can make out two faint outer rings, which according to researchers are the result of the interaction between the star's stellar wind emitted before the supernova and the matter previously ejected by the star. Unfortunately, the dust at the center of the supernova is so dense that not even the near-infrared light detected by the James Webb can penetrate it. That's why the keyhole is so dark in the photo. The telescope, although very advanced, was therefore unable to detect the supernova's residual star. Yet this is what scientists had hoped to observe. In fact, the collapse of a star's core, as happened with SN 1987A, usually leads to the formation of a neutron star or a black hole. In the case of this particular supernova, it would be a neutron star. Astronomers hope to be able to observe this neutron star once the gas and dust in the supernova's inner region have dissipated slightly. James Webb's next discovery we're going to talk about concerns Herbig-Haro objects, abbreviated as HH. Herbig-Haro objects are luminous regions surrounding newborn stars. When stellar winds or jets of gas spewed out by newly born stars create shock waves, and these shock waves collide at high speed with nearby gas and dust, Herbig-Haro objects are formed. On September 14, 2023, an image of the object Herbig-Haro 211, or HH211, was released. Located in the Perseus constellation, around 1,000 light-years from Earth, HH211 is a protostar that looks very much like our Sun when it was only a few tens of thousands of years old. Its mass is currently only 8% that of our Sun. HH211 had already been observed from the ground, but this is the first time we've been able to see it in such detail. The James Webb Telescope also photographed HH 797, an object located in the immediate vicinity of star cluster IC 348, at the edge of the Perseus molecular cloud, around 600 light-years from Earth. Observing this object from the ground, astronomers had noted that the cold molecular gas associated with HH 797 had a double motion. To the south, there was a redshift, meaning that the region was moving away from us. To the north, there was a blue shift, indicating that the region was moving towards us. Thanks to James Webb's observations, astronomers were able to distinguish two parallel jets instead of one, each with its own speed and history. This could mean that HH 797 is around a double star, and not, as astronomers have long assumed, a single star. Herbig-Haro objects are fascinating phenomena. The speed of the stellar winds and gas jets released by newly born stars is dizzying, and the shock waves created by the collision between these energies and the surrounding gas and dust are impressively powerful. These objects show us that within a star-forming zone, there are intense dynamics and energy flows that are both complex and incredible. With its infrared instruments like the NIRCam, the James Webb is perfectly equipped to observe newborn stars and Herbig-Haro objects, and thus better understand the dynamics at work during star formation. Let's continue our exploration of recent discoveries by the James Webb Telescope. On October 10, 2023, the James Webb observed the brightest star-forming region of the Small Magellanic Cloud, NGC 346. The Small Magellanic Cloud, also known as SMC or NGC 292, is a satellite galaxy of the Milky Way, and thus part of the local group, our group of galaxies. This irregular dwarf galaxy is visible to the naked eye in the southern constellation Toucan. It's one of the most distant objects visible to the naked eye, located some 199,000 light-years from Earth. In fact, you can only see it from the southern hemisphere, in a place far from pollution. The Small Magellanic Cloud should not be confused with the Large Magellanic Cloud, with which it forms a pair. The two are linked by the so-called Magellanic Bridge, a bridge of gas and stars. It's the small Magellanic Cloud that interests us here, as it was in this galaxy that the James Webb was able to observe NGC 346, a particularly bright star-forming region. This image of NGC 346 was taken by James Webb's MIRI instrument. NGC 346 is a region in which stars are regularly born. It has already been photographed by Hubble, so this is not the first time it has been observed by astronomers. However, the near-infrared images taken by James Webb in January, followed by mid-infrared images in October, have enabled us to refine our knowledge of this region. The James Webb images show bands of gas and dust, dotted with luminous spots, filled with young protostars. Astronomers were astonished that the images revealed cold gas and dust emissions. The small Magellanic Cloud is a more primitive galaxy than our own, so astronomers expected it to be fairly dust-poor. In fact, this neighboring galaxy contains fewer heavy elements than the Milky Way. Heavy elements are forged in stars by nuclear fusion and supernova explosions, so they appear late in a galaxy's lifespan. The small Magellanic Cloud must contain heavy elements, since it is heavy elements such as silicon and oxygen that are responsible for the formation of galactic dust. The James Webb images show polycyclic aromatic hydrocarbons and dusty silicates, as well as dust heated by the most massive and brightest stars, shown in red in the photos. Bright spots and filaments can also be seen, concealing a large number of protostars. The researchers counted 1,001 red stars, most of them young stars masked by dust. The images of NGC 346 are important because they will give us a better understanding of the more primitive galaxies that existed billions of years ago, at a time called cosmic noon, when star formation was at its peak and heavy elements were present, but in lower concentrations than today. Here is an image of another star-forming region taken by the James Webb's NIRCam, which immediately struck the general public with its sharpness and detail. This is Sagittarius C, or SGR-C, a star nursery at the center of the Milky Way. This image has made an indelible impression on the general public, as well as on researchers, because until now, infrared data on this region had never been obtained with such a high level of sensitivity. Offering unprecedented detail, the image revealed many previously unobserved features of this region. According to the researchers, the center of the Milky Way is the most extreme environment in our galaxy. Sagittarius C is located very close to the center, just 300 light-years from our galaxy's supermassive black hole, Sagittarius A. This star-forming region is therefore quite far from us, at 25,000 light-years from Earth. In this image, we can see around 500,000 stars and clusters of protostars, i.e., stars in the process of forming, or if you like, baby stars, and all in a volume about 50 light-years across. One of these protostars is particularly massive, with an estimated mass 30 times that of the Sun. This protostar blocks the light behind it, so James Webb was unable to see all the stars in Sagittarius C. This is a pity, as the area hidden by the massive protostar promises to be one of the densest. The darker areas visible in the image are also star nurseries. More precisely, they are Bok globules, i.e. dark clouds of dust and gas, in which the birth of stars can begin. But what most intrigues researchers is this region, shown in cyan blue, which extends over 25 light-years and is made up of ionized hydrogen. Typically, hydrogen is ionized by energetic photons emitted by massive young stars, but in this case, it's the sheer size of the area that has astronomers wondering. On top of this, researchers are puzzled by the needle-like structures seen in the photo, which appear to be oriented chaotically in several directions. These structures are astonishing, and for the moment, astronomers have no explanation. This is the first time such structures have been observed in the heart of the Milky Way. In any case, this highly detailed image confirms that the center of our galaxy is a tumultuous zone, boiling with energy. Clouds of magnetized gas form stars, which in turn emit stellar winds, jets, and radiation that impact on the surrounding gas and create impressive objects. An extreme environment that researchers are only just beginning to study. James Webb's detailed images will undoubtedly be a great help in the quest to understand star formation at the heart of our galaxy. Among James Webb's most significant discoveries at the end of 2023 was the discovery of a never-before-seen jet stream near the equator of Jupiter. This impressive discovery was made by comparing James Webb images with those from Hubble. It was subsequently published in the renowned journal Nature on October 19, 2023. It brought to light a feature of Jupiter that had never been seen before. According to NASA, it's a high-speed jet stream, moving at around 515 kilometers per hour, or 320 miles per hour, twice as fast as a Category 5 hurricane. In fact, it's a well-known phenomenon, even though it has never been observed on Jupiter before. A jet stream is a tube of strong winds located around 8 to 15 kilometers, or 9 miles in altitude, at the boundary between the troposphere and the stratosphere. The one detected by James Webb lies above Jupiter's equator, at around 40 kilometers or 25 miles above the clouds, and extends over 4,800 kilometers or 3,000 miles across. This discovery gives us our first glimpse of how the layers of Jupiter's atmosphere interact with each other. According to the researchers behind the study, published in the journal Nature, Jupiter has a complex pattern of winds and temperatures, and the jet stream that has been spotted could vary considerably over the next 2 to 4 years. It will be further studies by the James Webb that can help us determine whether the jet's speed and altitude tend to evolve over time. On July 27, 2022, the James Webb Telescope had already delivered unprecedented images of Jupiter. These were perfectly sharp, well-defined images, revealing details of the largest planet in our solar system, The James Webb images, taken with a NIRCam near-infrared camera, reveal Jupiter's rings, its smaller satellites, Amalthea and Adrastea, and above all its polar auroras, 100 times brighter than those seen on Earth. Jupiter's polar aurorae are caused by the encounter of matter thrown up from the moon Io with the gas giant's atmosphere. A study carried out in August 2021, using recordings from the Keck telescope in Hawaii, had shown that these aurorae acted like a radiator, providing heat to the whole planet. The James Webb images of Jupiter also show the famous red spot, which appears white because it reflects sunlight. Jupiter's Great Red Spot is a gigantic anticyclone in the planet's atmosphere, located at 22 degrees south latitude. Although it's not necessarily obvious from the James Webb images, this red spot is slightly larger than our planet itself. In 2015, its dimensions were estimated at around 15,000 kilometers, or 9,300 miles in length, and around 12,000 kilometers, or 7,500 miles in width. In the past, it would have been even larger, since it is estimated that over the course of the 20th century, it has shrunk by half. In this anticyclone, winds are said to blow at 700 kilometers per hour, or 430 miles per hour. The Great Red Spot was so named around 1878, but today it appears rather brown. James Webb did not discover this red spot, as it has been known for over 350 years, and very clear images of the phenomenon had already been obtained, notably by the Cassini-Huygens mission. However, these images will enable scientists to better study the interaction between the dynamics of Jupiter's atmosphere, chemical composition, and temperature in and above the Great Red Spot. Here are a number of images taken by James Webb and now well known to all astronomy enthusiasts. In this image, taken on July 12, 2022, you can see a young star-forming region in the Carina Nebula, 8,500 light-years from Earth. A region that had already been photographed by Hubble, but never with such precision. In this image, taken on September 12, 2022, you can see the Orion Nebula, the closest nebula to us at around 1,350 light-years from Earth. Once again, this region had already been photographed by Hubble, but James Webb's photo revealed new details. The image in front of you is very sharp. You can even make out Orion's bar, a wall of gas and dust inside the nebula, and two very bright stars that are part of the trapezium cluster. We can also see a cocoon of stars with a protoplanetary disk, conditions similar to those that led to the birth of our Sun and its planets 4.5 billion years ago. Another nebula was also photographed by James Webb on September 6, 2022, the Tarantula Nebula. Located 161,000 light-years from Earth in the dwarf-large Magellanic Cloud galaxy, this nebula is the largest and brightest star-forming region in the entire group of galaxies not far from the Milky Way. This nebula is also home to the hottest and most massive stars known. For all these reasons, the Tarantula Nebula is of great interest to scientists. Here's a final image taken in 2022, on July 12th to be precise, by the James Webb. It shows the Southern Ring Planetary Nebula, located around 2,500 light-years from Earth, in the constellation of the Veils. James Webb's image enabled scientists to discover the origin of this planetary nebula, a binary system of dying stars. On October 30th, 2023, the James Webb unveiled a new nebula image, the Crab Nebula. Located 6,500 light-years away in the constellation Taurus, this nebula is in fact a supernova remnant. The Crab Nebula had already been photographed by Hubble in 2005, but here again, the details provided by the James Webb images have enabled scientists to better understand its origin. The James Webb data have enabled us to establish the composition of the ejected material, in particular, its iron and nickel content, which will tell us what type of explosion produced the Crab Nebula. By the way, take a look at the two images side by side, the Hubble image and the James Webb image. You can see that in the James Webb image, there's more detail in the central regions of the nebula, where you can see the emission of dust grains. The orange filaments you can see in the image taken by the James Webb are the remains of a star that has now disappeared. The supernova created by the explosion of this star was seen on the Asian continent in 1054. For 23 days, the supernova shone brightly and could even be seen in broad daylight. Even today, the nebula continues to expand at a speed of 1,500 kilometers per second, or 930 miles per hour, as a result of this explosion. In the center of the image, you can see a translucent zone of what is known as synchrotron radiation. Synchrotron radiation is generated by the presence of a pulsar, a neutron star that rotates very rapidly and emits strong radiation. Thanks to these breathtaking details, scientists hope to glean valuable information for a better understanding of a star's life cycle. The image before your eyes is considered one of the most complete views of the universe ever obtained. This image has been reconstructed using James Webb and Hubble images. It shows the MAX 0416 galaxy cluster, 4.3 billion light-years away. More precisely, MAX 0416 is a pair of colliding galaxy clusters which will eventually merge to form an even larger cluster. Researchers combined images taken in visible light by the Hubble telescope and in infrared by the James Webb telescope to reconstruct this colorful view of our universe. In fact, why is this image so colorful? Quite simply, because it shows thousands of galaxies that appear differently colored according to the wavelength range in which they shine, i.e., from 0.4 to 5 microns. The nearest galaxies, regions of intense star formation, appear in blue and were detected by Hubble. The most distant galaxies, on the other hand, appear in red and were detected by James Webb, as they are too far away for Hubble to see. Objects colored green are located at mid-distance. James Webb didn't just take a picture of this cluster of galaxies at a given moment in time. He observed the region 4 times, a week apart, to identify what are known as transient objects. Transients are objects whose brightness varies over time. 14 transient objects were detected, 12 of which are likely to be single stars or multiple star systems, and 2 are likely to be supernovae. This means that transient phenomena could be much more numerous than previously thought. Among the transient phenomena identified in the MAX 0416 cluster, one in particular has caught the attention of scientists. This is a giant star that has been nicknamed Mothra because of its monstrous nature. It is located in a galaxy that existed some 3 billion years after the Big Bang and is amplified by a factor of at least 4,000 through gravitational lensing. Mothra was already visible in Hubble's observations almost 10 years ago, which is quite unusual. Indeed, it would take a very specific alignment between the galaxy cluster in the foreground and this star in the background for it to be so amplified. However, the mutual movements of the star and the cluster should have broken this alignment. The explanation put forward by the scientists is the presence of an additional object in the foreground group, which would add magnification, like a globular cluster. This object would have a mass between 10,000 and 1 million times that of our Sun. The MAX 0416 cluster has been nicknamed the Christmas tree cluster because, according to NASA researchers, it is very colorful with flickering lights, like the lights on the tinsel of a Christmas tree. Among the most recent images taken by the James Webb is this impressive photograph. This is no trick. This cosmic ghostly figure is a galaxy in formation called Aztec 71, more precisely, a dusty star-forming galaxy. This is a type of galaxy hitherto reputed to be very rare and almost invisible. Hubble had already attempted to photograph this galaxy in formation, but without any real success. Aztec 71 is very difficult to observe. This galaxy is the seat of star formation, but it's shrouded in a dusty veil that's very difficult to penetrate. That's why Hubble, which couldn't see in the infrared like James Webb, wasn't able to obtain satisfactory images. James Webb's image, broadcast on October 10, 2023, is very striking. It looks like a ghostly face. It looks like a tiny drop in the vastness of the universe. But this galaxy is actually forming hundreds of new stars every year. This discovery shows us that there could be a whole population of galaxies hiding from us that we won't be able to observe until we develop even more powerful instruments than the James Webb, capable of seeing in even more extreme wavelengths. This discovery has also led researchers to claim that this type of galaxy, thought to be extremely rare, is in fact 3 to 10 times more common than previously thought. Like the image you've just seen, this photo of the exoplanet WASP 107b, taken by the James Webb, is also very impressive. WASP 107b is a gas giant, orbiting a highly active K-type main sequence star. located around 200 light-years from Earth. It is nicknamed the Hot Super Neptune. One of its special features is that it is one of the exoplanets with the lowest known density. Its mass is only 12% that of Jupiter, while its diameter is comparable. This is due to the fact that its atmosphere is greatly expanded by the radioactive heating of its star, around which it orbits in just 6 days. Temperatures in its atmosphere reach hundreds of degrees. WASP-107b's highly expanded atmosphere has earned it the nickname of Cotton Candy Planet. In any case, it facilitates measurements of the planet's atmospheric spectrum. Astronomers had already discovered helium in its atmosphere thanks to Hubble's observations. Observations by the James Webb have taught us new things about this cotton candy exoplanet. The data provided by the telescope was analyzed by a team of European astronomers, co-led by researchers from CEA and the Institute of Astronomy at the Belgian University KU Leuven. The scientists were able to detect silicate clouds in WASP-107b's atmosphere, a first for a planet of this type. According to their analysis, WASP-107b's atmosphere contains not only clouds of silicate particles, cousins of sand grains, but also molecules of water vapor and sulfur dioxide, SO2. Surprisingly, however, no traces of methane were found. This remains unexplained for the moment, unlike other discoveries such as sulfur dioxide, which have been elucidated by new models. Astrophysicists still don't understand why no trace of methane has been detected in the atmosphere of WASP-107b, which might force them to revise the models of exoplanet atmospheres known to date. Nevertheless, if the discovery of silicate clouds initially surprised scientists, it can be explained. What astonished astronomers was the presence of these clouds at high altitude. The temperature is only 500 degrees Celsius or 930 degrees Fahrenheit at this altitude, yet the melting temperature of silicate particles tells us that they should form deeper in the atmosphere at higher temperatures. Surprisingly, sand clouds exist and persist at high altitudes. In fact, it would seem that the phenomenon is roughly similar to that of the water cycle on Earth, except that rain is not made up of drops of water but of sand. The droplets of sand rain evaporate into deeper, hotter layers, and the resulting silicate vapor is then carried upwards, where it recondenses to form silicate clouds once again. A discovery that overturns our understanding of exoplanet atmospheres. WASP-107b appears to be an exotic world, completely different from our own, with complex chemical interactions. There is no equivalent of this exotic world in our solar system, and that's what's so fascinating. Here's another image that may not mean much to you, but represents a real breakthrough for astrophysicists. This image is none other than the discovery by the James Webb Telescope of the most distant black hole ever detected in X-rays. This discovery was made possible by the combination of two space telescopes, the James Webb and Chandra. Because it emits X-rays, we know that it is a supermassive black hole in full growth. The study of this black hole will be invaluable in understanding how some of the first supermassive black holes in our universe were formed. Most astrophysicists agree that there are compact stars at the heart of the vast majority of large galaxies, containing at least 1 million and sometimes several billion solar masses, and behaving as predicted by black hole theory. In other words, supermassive black holes. What we don't know is how these supermassive black holes came to be. There are a number of theories. One of the most widely accepted is that black holes are formed by the accretion of matter from cold filaments. What are cold filaments? They are filaments of cold gas, channeled by filaments of dark matter, which are thought to feed the star-forming matter that makes galaxies grow. Many other hypotheses have been considered. The existence of primordial stars of very high mass, the existence of giant black holes produced during the Big Bang. The discoveries of the James Webb Telescope should enable us to find out more. Let's return to our image. First, Chandra, a space telescope in orbit since 1999, detected a source of X-rays in the UHZ1 galaxy, in the direction of the Abel 2744 or Pandora cluster of galaxies, 3.5 billion light-years from the Milky Way. The Pandora cluster, thought to have resulted from the merger of 4 smaller galaxy clusters, is particularly rich in dark matter. This creates a useful gravitational lensing effect for astronomers, making it easier to observe distant galaxies in the visible or near-infrared range. From the data collected by James Webb, researchers were able to establish that galaxy UHZ1 is seen as it was only 470 million years after the Big Bang. As for the Chandra data, they show that the X-ray source associated with this galaxy has all the characteristics of a growing supermassive black hole. This would make it the most distant black hole ever observed in X-rays. What's more, this black hole would have unusual characteristics. With a mass 10 to 100 million times that of the Sun, it contains a quantity of matter equivalent to that of all the stars in the galaxy where it lived in a past revealed to us by photons that traveled more than 13 billion years. We are therefore observing a black hole at an extremely early stage, with a mass similar to that of its host galaxy. According to the researchers, this is a very brief phase in the life of a black hole, during which it weighs about as much as the stars in its galaxy, before falling behind. All these observations confirm the hypothesis that supermassive black holes are the result of a gravitational collapse of a very large gas cloud. Since its launch at the end of 2021, the James Webb Telescope has enabled numerous advances in the fields of cosmology and astrophysics. Not only have new cosmic objects been discovered, but even more knowledge has been gained about the objects already photographed by Hubble, with captivating, colorful images packed with detail. The discoveries made by the James Webb have provided new insights that will not only help us better understand certain cosmic phenomena, but also advance our understanding of the phenomena at the origin of our universe. Here's a first example. In a study published on November 8, 2023, in the journal Astrophysical Journal Letters, a team of researchers explained the role of protoplanetary disks in planet formation deduced from observations of the James Webb. Protoplanetary disks are agglomerations of gas and dust. They are home to icy rocks, which release water vapors under the effect of extreme temperatures. Protoplanetary disks are therefore predominantly composed of cold water. As they approach newborn stars, icy rocks evaporate, forming rocky planets. This phenomenon was certainly behind the creation of our solar system some 4.6 billion years ago. This hypothesis suggests that even in the most extreme environments of our galaxy, where protoplanetary disks are found, telluric planets like our own could form, which considerably widens the field of possibilities. Here's a second example of a discovery made thanks to the James Webb that has profoundly changed the theories of modern astrophysics. In the vicinity of the Big Dipper constellation, the James Webb Telescope has captured some very old galaxies that, according to our current theories, shouldn't even exist. The 6 galaxies discovered by the James Webb are estimated to have formed only 500 to 7 million years after the Big Bang. They are therefore almost 13 billion years old. However, according to the researchers' calculations, they could contain as many stars as the Milky Way, which doesn't fit our current models. According to currently accepted theories, there must not have been enough matter at that time for galaxies to form as many stars as the Milky Way. These discoveries call into question the very principle of the formation of the first galaxies. At first, because James Webb had already observed very old galaxies, formed around 350 million years after the Big Bang, but they were small and didn't contain as many stars. Galaxies that are both very old and massive, never before seen. It's possible that the red dots observed by the researchers are not very old galaxies, but quasars or supermassive black holes. Or they could be smaller galaxies than scientists have calculated. New data will be needed to confirm the discoveries and find out whether or not we need to revise our current theories and models. New data, that's what we're waiting for to complete all the somewhat disturbing discoveries made over the last 2 years by the telescope. Scientists are keen to make the most of James Webb's potential and use its mission to confirm and refute each of these strange discoveries. Above all, these observations are expected to enable us to reconstruct the history of the universe without any blanks. In fact, the ultimate goal is to fill in all the gaps in our understanding of the universe. How did the universe ignite? How did galaxies come into being? At present, we still don't know how to go back to the first instance of the universe. It's as if we had photos of the universe as a baby, arriving home from the maternity ward, but not of its very first moments. The very first memory we have of the birth of the universe is when it is 378,000 years old. The universe is then what we call the cosmic microwave background. It's made up of tiny specks, representing variations in density. The densest regions become galaxies and stars until they reach us. But how did these tiny specks create galaxies and stars? This period, which lasted several 100 million years when stars didn't yet exist, is known as the Dark Age of the universe. The universe was made up mainly of hydrogen, like a fog in the end, since hydrogen atoms reflect light radiation and we can't see through them. Our knowledge of the history of the universe lacks that moment when the universe emerges from the Dark Ages and the first stars and galaxies begin to take shape. This is what we'd like to understand with James Webb and future generations of telescopes.